All right. So good afternoon, everyone. This is the lecture number 6 or 7, I believe. And let us, as usual, go quickly through the material that we discussed last week. Where is the... Okay. Yeah, so it was lecture number 5. And so basically last time we continued the discussion of the basics of quantum mechanics, and we started with the evolution of quantum system, right? So as we discussed many times already, the state of the quantum system is represented by the psi vector or state vector psi, and and the evaluation we postulated, right? Or actually it was it has been done by Schrödinger, who postulated this equation that governs the evolution of the psi state in time. So there are several key points here. The first one is that, as we can see, the time evolution of psi vector or the state of a quantum system is mainly given by this H operator, which is Hamiltonian operator. Hamiltonian operator is an operator of energy of a system, and it is one needs to, when you start when one starts describing a quantum system, one needs to predict or establish, state this Hilbert operator, and then see if the results of the calculation coincide or in agreement with the experimental results, etc. Also, this equation is single. This equation is first order on the time derivative, in contrast to, for example, the wave equation, but contains this imaginary unit on the left side. So the imaginary unit here in this equation allows this equation to have harmonic solutions in form of sine and cosine or exponential function to the power of I omega t. Okay. Yeah, so this Schrödinger equation it describes the time evolution of any quantum system. Okay. Then we also wrote down the equation for the dagger, for the Hermitian conjugated version of the Schrödinger equation. Then we discussed the Hamiltonian for the particle, like electron, in a potential V. Okay. Then, yes, then we derived the stationary state solution of the Schrödinger equation. So we basically say that if the Hamiltonian has no dependence on the time, okay, then the evolution of the system can be kind of split into two parts. One depends on the special part, the like coordinate of a particle or something like that. So this part doesn't depend on the time. I'm talking about specifically about this phi here. Okay, and the second part, which is kappa, that depends only on time and no dependence on the coordinates. Okay, so in this case, the variables can be split it, right? And solution can be written in this general form. So the solution to the Schrödinger equation in the steady state regime is given by a product of the special part and the harmonic part, which is e to the power of minus I e over h bar t. Okay, harmonic part of the solution. Then we solve this textbook problem for a particle in an infinitely deep potential well. Okay, we have shown how in this particular case the energy is quantized. So instead of a continuum of energy states, like for a particle in a free space, when we put the particle inside the well, the energy becomes quantized. We derive the spectrum of this energy spectrum, and yeah, so the particle, so the energy is gets the discrete levels, allowed levels. Then we discussed how this relates to real life applications like a quantum dot. A quantum dot, in fact, is a quantum well with a charged particle in it, and the particle gets the discrete spectrum, and for example it can emit light when this electron, the particle, transits between the states. It can emit photon or absorb photon, and we really use this type of quantum systems in many applications actually. Then we discuss this, then we start discussing these mixed states and their difference comparing to the pure states. So thus far, all our examples were about one isolated quantum system, which can be described by the state of which can be described by this psi vector. Okay, but in reality, our state can be either our system, this particular system can be actually one of the many systems in an ensemble, like an electron in a cloud of electrons, or quantum dot in a system of many, in an array of quantum dots, or like one quantum well within many other quantum wells. Okay, and even though the state of each of these quantum systems described by their own psi vector, we still have a lack of knowledge about the entire system because they differ in terms of position, velocities, momentum, conditions, many things. Okay, so we need to bring this classical concept of probability distribution to the picture. So we need to average all the observables, not only using psi vector or like quantum, this probability in terms of in quantum terms, but also this classical probability, which comes because we have not the entire whole information about the particular system. Okay, and another example when we need to bring this mixed state analysis is a system that interacts with the other systems, like it can be, for example, a quantum dot that interacts with the environment. Okay, this quantum dot needs to be placed somewhere, and it can be some kind of a matrix or a substrate or I mean whatever. And this substrate or this environment, of course, interacts with the quantum system, with this quantum dot, as an example. And of course, we cannot describe rigorously this interaction. Okay, we need to average this interaction of a quantum system with a classical, with this environment. So we need to bring this density operator to the analysis. Okay, so here is the way how we introduce the density operator, density matrix. Okay, so it basically means given by this red framed formula here, where P is the classical probability. Okay, it can be Maxwell distribution or Boltzmann distribution or something else, such as classical distribution. And this outer product of two psi vectors for each subsystem, for each quantum subsystem I here. Okay. Important result was that in order to calculate the average, the mean value of a observable A, we need to take the trace of the density operator with the operator of the observable. For example, if this observable is energy, then we need to take the trace of the density operator with the energy operator, which is Hamiltonian. Okay. Momentum, you just replace in this formula, you just replace this A operator with momentum operator, and you get the formula for the mean value of the momentum, and so on. And we concluded the last lecture with the discussion of several properties of density matrix. Some of them are rather trivial. For example, the fact that density matrix is a Hermitian operator. This just comes from the definition. Trace of the density operator is 1. Okay, so it's also rather trivial. This comes from the fact that the probability being summed up over all the possible states is equal to 1, right? So the probability is normalized to 1. Another property is that for a pure state, the density operator squared equals to the density operator. Again, this kind of trivial, comes from the fact that the psi vector has norm 1, right? So the length of the state vector is always 1. So we normalize it this way. And the last one, which is less trivial, and I don't give a proof of this one, but at the same time, it's pretty useful one. So the property number 4 states that for the pure state, the trace of the square of the density operator is equal to 1. And for a mixed state, this quantity, this trace of the rho squared, is less than 1. It actually means that for some system, if you know the density matrix, for example, you calculate it or measured it, or this is a result of some computation, for example, you can check the pureness of the quantum state. Is it pure state or the mixed state? Okay, and now as a few examples, let us consider few problems to to practice this one. And the first example example one for today is the density matrix of a qubit in a pure state. Density matrix of a qubit in a pure state. So the concept of density matrix is a more general one, and one can use density matrix to describe not only mixed state but also a pure state, as we discussed. And so yeah, let us derive this density matrix for a qubit in any general pure state. So the psi vector of a qubit, as we discussed many times, is the first coefficient C naught state 0 plus C1 state 1, right? Where state 0 is the column 1, 0, state 1 is column 0, 1. Okay, and C0 and C1 give us the projections of a psi vector on the basis vectors 0 and 1. Okay, so by definition, the density operator is a sum of over different quantum systems or subsystems with different classical probabilities, and the outer products of psi states. Okay, but in our case we have only one single qubit, so in our case the density matrix or density operator is given by simple product psi times psi. Okay, and yeah, so let us write the vector bra for a qubit. So it's gonna be 0 bra, C0, we can write it like the C0 complex conjugated 0 plus C1 complex conjugated 1, right? So I just took the dagger or Hermitian conjugation of this general state of a qubit. And now let's plug in the above to this formula of the density operator. So it's gonna be ket C0 0 plus C1 1, and the second one is C0 conjugated 0 plus C1 conjugated 1. Okay, so let us take the product and expand the parentheses. So we get C0 conjugated product 0 0 plus C0 C1 conjugated state 0 1 plus state C1 C0 complex conjugated 1 0 plus C1 C1 conjugated 1 1. Okay, Now I can rewrite this in the matrix form. C0 conjugated is absolute value squared, C0. The second component is C0, C1 conjugated. The third is C1, C0 conjugated. And finally C1 squared. Okay. So yeah, so this is the density matrix of a qubit in a pure state. So should we write it as a formula? So the density matrix in a pure state is C0 square, C0, C1, C1, C0, C1. Okay. So what is the physical meaning behind these coefficients? Okay, so we have here we have the diagonal components, which are C0 square and C1 square. Right, so diagonal components. These diagonal components give us the probability of finding the qubit in a corresponding state. Give a probability of finding qubit in states 0 and 1. Okay. And off diagonal elements. So out diagonal elements C0, C1 conjugated and C1, C0 conjugated. We see that these two, they are complex conjugated versions of each other, right? They connected through complex conjugation. And these coefficients describe the quantum interference. Let's use this word. Quantum interference. So what I mean by this? So the state of a qubit can be represented by, for example, two separate energy states of the qubit. Okay, so for example, this 0 state and state 1, they are they have different energy. So usually we set the, I mean, we name the first state, which is the ground state, or the state with the lowest energy is the state 0, and the state with the higher energy is the state 1. Okay, and we can somehow test the qubit in a state 0, for example, and finding this excitation with the state 0. For example, it can be electron, right? Electron on the 0 state is given by C0 model squared. Sometimes this electron could be found in the state 1, and the probability of this is C1 squared, model squared. Okay, but the fact that the electron or this excitation can transit between the states from 0 to state 1 and from 1 to state 0 means that these levels, they kind of interact. Okay, so these states, they interact. They have a finite overlap. Okay, and in this language, this is the result of the interference of this quantum interference of the of the separate states. Okay, so this is described by C0, C1, C0, C1. Okay, for example, transition from 0 to 1 will be given by C0, C1 conjugated. The back transition from state 1 to state 0 will be given by the second component, C1, C0 conjugated. And the fact that these two components related through the complex conjugation reflects the fact that this transition from 0 to 1, from 1 to 0 is equivalently possible. Okay. Okay, so do you have any questions regarding this part? Okay, if not, let me consider another example. Example 2, let's take something very basic. For example, we consider different basis states, state 0, state 1, and for example, state plus. Okay. So what is the density matrix that corresponds to these three different states? So for the 0 state, what we get 0 times 0, right? Which is 1, 0, 0, 0. Likewise, for the state 1, we have 1, 1. So it's gonna be 1. It's gonna be 0, 0, 0, 1. Okay. And finally, for the state plus, we have the density operator plus. Okay. Or 1 square root over 2. Cat is 0 state plus state 1 times bra, which is 1 square root over 2, bra 0 plus bra 1. Okay, so 1 over square root over 2 taken twice give me 1 over 1/2, and this give me 4 terms. The parentheses give me 4 terms: 0, 0 plus 0, 1 plus 1, 0 and plus 1, 1. Okay, so the result is 1/2 and matrix 1, 1, 1, 1. Okay, so this is the density matrix for the state 0, for the state 1, and for the state plus. And likewise, one can find the density matrix in any other cases. And so far, of course, we're talking about the poor state. Okay, so all these states so far are poor. But let us consider another example or problem 3. And let me give you density matrix, which has components 0.6, 0.4, 0.4, and 1.4. Okay, so I noticed that and the problem is to check if this is pure or mixed. Okay, so for example, your, let's say, I don't know, quantum computer gave you this answer, and you need to check if this is the pure or mixed state, and the degree of it. I mean, if it's mixed, then what is the degree of this state to like in this mixed state. First, what I do, I check if the density matrix is normalized, right? To do so, I calculate the trace of the density matrix. And for this particular one, it's 0.6 plus 0.4, right? Which is 1. Okay, so the density matrix is normalized, and I don't need to normalize this one. Okay. Yeah, so and now we can check if this state is, if this matrix is a matrix of a pure or mixed state. To do so, we use the property number 4. Okay, so we need to calculate the trace of the square of density matrix, and if it's equal to 1, then the state is pure. If it's less than 1, then the state is mixed. Okay, so what I need to do, I need to take the square of density matrix. So I just take the matrix product of the two, 0.6, 0.4, 0.4, 0.4, and the second one is exactly the same, 0.6, 0.4, 0.4, 0.4. Okay, so let's take as the matrix product. So 0.6, 0.6, it's 0.36, right? Plus 0.4 times 0.4 is 0.6, 0.4, 0.4. It's 0.16. Let me see. Sorry, this one is 32, and this one is 32. This one is 16, right? Yeah. So for the next one is 0.6. Excuse me?
You sure it wasn't 36.36?
So let me, yeah, so 0.6 times 0.6 is 0.632, right? Let me, sorry, I'm 0.6 times 0.6. Oh, yeah, 36. And then 0.4 times 0.4 is 0.16. Okay. Okay. Then the next one is 0.6 times 0.4 plus 0.4 times 0.4 times 0.4. Yeah. Then 0.4 times 0.6 plus 0.4 times 0.4, and finally 0.4 squared plus 0.4 squared, right? Looks good. So 0.36 plus 16, 0.36 plus 16 is 0.42, oh, 52. Next, 0.4 squared 0.16. Oh, okay, of course. And this one is 0.6 times 0.4, 0.24, and plus 0.16, 0.4, 0.4. This one is also 0.4. And finally, 0.16 plus 0.16.
32.
Yeah, 0.32. Okay. Yeah, so this is the density matrix squared. And now we calculate the trace of this one. Right, so it's a 0.52 plus 0.32. 0.52, which is 0.84. 84. So it is less than 1, and it means that this particular state is a mixed state. Okay. The state is mixed. The state is mixed. Okay, and this is kind of 84%, right? 0.84 differs from the 1, like 84%, which means that it is, even though it's a mixed state, it's pretty close to being a pure state. Okay, so let us maybe consider another example. So example number 4. Example number 4. And let us take another density matrix, like 0.7. So this one's supposed to be 0.3 to be normalized. And I need to consider a complex number, so I put like 1 plus I here. And density matrix must be a Hermitian conjugation, Hermitian matrix. So the last one, this one must be 1 minus I, right? Complex conjugated number. And the problem is to find the probability of measuring the state, find the probability of measuring the state in 0 and 1, in the states 0 and 1. Okay, so we have a state which is described by this density matrix. Okay, and then we measure this system in the 0 state or 1 state. Okay, and yeah, so and what is the probability of finding the system in the 0 state or 1 state after the measurement? Again, this 0 or 1 can be the orientation of the magnetic field, and this density matrix can be the state of the spin. Okay, and we measure the spin in the 0-1 basis. And what is the probability of finding the system in the 0 state after the measurement or in the state 1 after the measurement? Okay, so what we yeah, again, so the trace of this density matrix is 1, so we don't need to normalize it. Okay, and for the basis vectors, so density matrix, by definition, density matrix is no, let us say this way. So by definition, the mean value, the expectation value of a observable is given by the trace of the density matrix times the operator that represents the observable, right? So this is the expectation value of any observable. In our case, our expectation value is either 0 or 1. So let us denote this state either 0 or 1 by vector n. So this is 0 or 1. Okay, so it's a state. And hence the corresponding operator of this state will be n cross n, right? This is the outer product of the n. So this is the operator that describes the that our observable, either 0 or 1. Okay, and hence the probability of finding the system in either state n will be equal to trace of the density matrix times the operator n. Okay, looks good. Okay, so for the state 0, we can rewrite this replacing n by 0. So it's rho and state and the operator 0, 0. Okay, and let's plug in the density matrix here. So it is 0.7, 1 plus I, 1 minus I, 0, 3, and times the matrix 0, 0, which is 1, 0, 0, 0. And we will need to take the trace of this. So let's take the the matrix product. So it's a trace. The matrix will be, so the first one is 0.7, right? And then times 0 is 0. This one is 0. This one is 1 minus I. And the last one is 0. Okay, and the trace is equal to 0.7 plus 0 is 0.7. Okay, so this is the probability of finding the state, finding the system in the state 0 after the measurement. Okay, this state 0 can be, for example, vertical polarization of a spin, and this is the probability. And likewise for the state 1, we get trace, we get the same density operator plus I 1 minus I 0.3, and the matrix that corresponds to the operator 1, I mean 1 1 is 0 0 0 1. Okay, so it's gonna be trace. The first one is 0, second is 1 plus I, this one is 0, this one is 0.3. So the answer is 0.3 for the trace. Okay, and as we expected, the P0 plus P1 is equal to 1. So it is indeed probability. So the probability is normalized to be 1. Okay, so this is the introduction of the density matrix and how we work with density matrices. So usually this part also requires some discussion about the decay and dephasing, because it is kind of important for the future, for the rest of the course and for the quantum physics as a whole. But unfortunately, it requires like a lot of math and time. So let me, since this is the introduction to quantum, right? Let me just state several things about the decay and dephasing and how it's related to the density matrix. Okay, so let us discuss. Let us discuss decay and dephasing. Okay, because at the end of the day, the reason why we need density matrix is the fact that any quantum system, like a quantum computer, is of course subject to interactions with, let's say, environment, or with some noise. Or another reason is that the quantum computer works at the finite temperature. For example, these cryogenic computers, they are cooled to very low temperature, usually like maybe 10 millikelvin, but still the temperature is finite, and still this finite temperature provides some source of noise, and this noise is the main reason for dephasing, and dephasing leads to the loss of information, like quantum information. So, and this is described by, this process is described by density matrix, but it requires some math. So let us quickly discuss on a on a simple level how it works and how it's discussed, and introduce two important parameters here. So let us suppose that we have a qubit, okay, and this qubit gets two states, like state 0 and state 1, okay, and this system can be, for example, literally it can be a qubit of any kind. We can, for example, talk about a spin, for example. Okay, so it's something that we already discussed, a spin. And the fact that zero state is like lowest energy, state 1 is this higher energy. It simply means that the different orientation of the spin, for example, in the magnetic field, is it has different energy. Okay, and I can excite the system by applying some pulse. For example, pulse of electromagnetic field. Okay, and the result of this pulse, the system, this qubit, will transit to the excited state. Okay, but what happens after that? So we excited the qubit. What happens after that? So in the later instance, when the excitation pulse went through the structure, through the qubit, we left with the excitation in the upper state. Okay, so for example, spin is reversed to the opposite direction. So it is now in the upper state. And what happens to this qubit, to this state? It actually oscillates. Being in this upper state, it oscillates like this with some decay. Okay, so usually it's exponential decay like this. So this is over time. So this polarization of the qubit oscillates and decays in time. For example, you can imagine an atom, like hydrogen atom, and if you excite the hydrogen atom with a low energy pulse, so energy is not enough to cause any energy transitions, okay? So the atom will still acquire some polarization. It will polarize and then oscillate. And this oscillation, of course, causes the photons scatter. Okay, so this is just usual scattering of an atom without transitions. And this process, this decay of phase of polarization, is called dephasing. Okay, so this is dephasing. Dephasing. And the dephasing of a state can be in the ground state or in this excited state. So this is just about keeping the phase of the field or the pulse that caused this polarization. Okay, so this oscillation of the qubit, of the state of the qubit, remembers the state of the excitation pulse. Okay, but after some time, the qubit loses this information about the pulse, and this process is known as dephasing. Okay, so this is dephasing, and the dephasing time is called T2 star. So this star here is not complex conjugation, it's just a way how we distinguish between this pure dephasing and something that we're gonna discuss in a few minutes. Okay, so dephasing is one process here, and there is another one, another process is the decay of the energy. So as we discussed, when we excite the qubit from the ground state to the excited state here, of course, the system tends to the lowest possible energy, right? And the qubit must decay spontaneously to the ground state. Okay, so after some time, which is known as time t1, the qubit decays from the excited state to the ground state. So this is t1, and the process is known as decay. Okay, so decay and dephasing, dephasing and decay. Dephasing is a process when the qubit gets decoherence, so it loses the information of the excitation pulse. And decay is the process of decay of energy decay. Okay, so the energy state 1 collapses to the state 0. And these two processes are not completely separate, but we still can distinguish them. For example, usually dephasing is much, usually dephasing is faster. Okay, so the system usually loses the phase quicker than decay, than the loss of the energy. So the energy can be in the system, in the qubit, but it's already, lost the polarization state. Okay, so usually T1 is larger than T2 star. And let us write this down again. So T1 is the decay time. T2 is the pure dephasing. T2 star. And T2 without the star is known as decoherence. Okay, so this is the terminology. So the fact, the reason why we have two different T2s is that the total decoherence, which is given by the ratio 1 over T2, 1 over decoherence time, is equal to 1 over 2T1. So it's decay time plus 1 over T2 star. Okay. So this is simply a manifestation of the fact that both decay and dephasing lead to decoherence. Okay, the total decoherence depends or defined by both decay and dephasing. Okay, so this T2 is I would say, one of the main parameters of any qubit. And as we will see today, for example, these IBM quantum computers, they state this T1 and T2 on their website. So you can estimate how long the quantum information lives, or how long a particular quantum computer keeps the quantum coherence. Okay, so this decoherence time basically defines the time over which the quantum algorithm can be executed. Okay, so execution of a quantum program needs some time, right? It's execution time. So if this execution time is larger, for example, than the T2 of a particular quantum computer, then it means that that quantum computer is not good enough to run the problem. So any quantum algorithm, the execution time of any quantum algorithm must be less than the decoherence time of a quantum computer. Okay, and yeah, as I said, rigorously these processes are described by density metrics, and these T1 and T2, they appear as parameters in the final formulas for the density matrices. And for example, if you have a state psi, right? After excitation, decay of this state psi can be written as a psi naught. So it's a state psi at the time moment 0. for example, right after the excitation. And then the state, for example, collapses like T over T2. Okay, so this T2 is the decoherence time here. And yeah, so using this approach, one can introduce this T1 and T2 in the formulas for the density matrix. And let us also write this down, that after T2, a quantum coherence and quantum information is lost. Yeah. Oops. Quantum coherence and quantum information is lost. So the larger T2, the better. Okay. So many groups around the world really strive to develop a system with a large T2, because larger T2 will allow us to execute more complex quantum problems. Okay. All right. So this is about the pure states and mixed states. And the final postulate, which is postulate number 10, I believe. Postulate number 10 is about composite systems, is about quantum entanglement. So let us give it a name like description of composite systems. Quantum entanglement. So it's last postulate in this introduction. Okay. So, well, we already discussed when we were discussing the tensor product, right? We mentioned that if we have, for example, two systems, one described by psi vector 1 in Hilbert space V1, so it's a complex linear space of complex vectors, and we have another space with another vectors psi2 in space V2. For example, it can be two different qubits. Okay, two state quantum systems. Each of them live in its own Hilbert space. The system 1 lives in the space V1. The qubit 2 lives in the space V2. Okay, and so the question is how to describe a combined system, combine of both. And to do so, we introduce a tensor product of the two spaces. So the new space where live the all possible states of the resulting two component system. Okay, the new space is given by the tensor product of V1 and V2. So what is this tensor product of two spaces? It's simply a tensor product of the corresponding vectors. So you basically take every vector in the space 1 and take the tensor product with the vector from the space 2, and as a result, if you had a two-dimensional space, right, if both spaces are two-dimensional, the result it will be the four-dimensional space. Okay, so let us write it like this. So that the resulting psi vector in the new space without index here is given by psi1 tensor psi2. Okay. Also for simplicity, we usually don't write this tensor product sign, and we could write something like psi1 psi2. Okay, or even to make it even like more manageable, we can write like state psi1 psi2. Okay, so it's kind of one single state which denotes the state in a new space. For example, if I have psi1 in the first space AB and the vector 2 with components C and D, okay, so the new vector will be given by like this. So it's a tensor product of the two. And the result is given by the tensor product of two vectors. Okay, so I just remind you that tensor product of two vectors is a product of each component of the first vector by the second vector. A times the second vector, B times the second vector. It's a new vector. And indeed, we've got the a new vector with four components: A, C, A, D, B, C, and B, D. Okay. So again, we had two qubits, one with states A and B, another qubit with states C and D. They are separate, and then we bring them together, and as these two systems together, we can introduce a system of larger dimension, a space of a larger dimension. In this case, we need to use the space of dimension 4, and take the tensor product of the vectors. So we get the vector in the Hilbert 4-dimension space, in the 4D space. And now this new vector, the 4-component vector, describes the state of a resulting system. Likewise, we have to generalize all the operators and matrices. For example, like matrix A with components 1, 1, 1, 2, 2, 1, 2, 2. And for the first qubit, right, and the operator B with components B1, 1, B1, 2, 2, 1, and 2, 2. It's an operator that acts on the second qubit. The resulting operator that acts on the both qubits will be given by the tensor product of the both operators. Okay, and again, it's just the product of every component of the first one by the second operator. 1, 2 operator B, 2, 1 operator B, 2, 2 operator B. And if we expand these products, we will get the matrix 4 by 4. Okay, let me skip this writing. Yeah, so this is the way how we generalize the description from 2.2 dimension Hilbert space and a qubit to a large dimensions. For example, if I take a third qubit, it's gonna be a double tensor product. So the resulting dimension will be 2 to the power of 3, which is 8, and my vectors will be will contain 8 components. Okay, and all the matrices will be matrices 8 by 8, and so on. Like a system of 10 qubits will be a system will require to so a system of 10 qubits. To describe a system of 10 qubits, we will need vectors with number of components 2 to the power of 10. Okay, and the matrices will be 2 to the power of 10 by 2 to the power of 10, which is a colossal huge number. Okay, so the key point to understand here is so if we have two quantum systems, like two qubits, A and B, and for now let's consider them without interaction. So no interaction, like no coupling, no interaction between them. Still, in order to describe this entire system, I need to write the tensor product of the two. So the psi state of the entire system will be psi A times psi B, right? And for the psi A, let me write C, let me see, 0 A, zero A. Yeah, let's use this notation. Plus C1B 1B. So that's for the first one, times C0B. Oops. Sorry, it's supposed to be A. C0B 0B plus C1B 1B. Okay, so it's just the product of two states of the corresponding qubits. Qubit A, qubit B. It can be each one. Either one can be in the state 0 with probability C0, or in the state 1 with probability C1. Okay, so the product of the two will be C0A, C0B. Yeah, and then here 0A, 0B plus C0A, C1B 0A1B plus C1A, 0b 1a 0b plus c1a c1b state 1a and 1b. Okay, so we see that if we consider now the system in the four-dimensional space with the basis vectors 0, 0, 0, 1, 1, 0, 1, 1. Okay, this new resulting vector is given by the projections, these coefficients, right? So we have 4 components. That's what we expected to get. So the psi vector of our system is given by C1, 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 C2, C2, C1, C2, C2. Okay. But I remind you that this is for no interaction, no interaction. No interaction or weak interaction. The point here is that we still can separate the things. Like we can say, we can tell that, oops, this is supposed to be 0, 0, 0, 1, 1, 0, and 1, 1. Yes, sorry for this. So we can separate the coefficients, right? So for example, C0A from C0B and so on. So we can separate the state of each system. We can distinguish the parts. So what happens when we turn on the excitation, turn on the interaction? So with interaction, we can no longer distinguish between C0A, C0B, and etc. And these products of the coefficients become undistinguishable. Okay, so for example, when we turn on the interaction, the new state, the new vector, will be given by still by 4 elements, but written like this. For example, C00, C01, C10, C11. So it's no longer the product of the coefficients from corresponding to each system, A or B. Now it's a coefficient that is not, is not separate. Is not separate. You cannot separate the things. You cannot separate the subsystems because they interact. So, and this is the manifestation of the simple fact that the systems interact. So because the state of one subsystem depends on the state of the other system, because the state of A depends on B and vice versa. Okay. So this is the result of the interaction. And let us, for example, consider a very important, particularly important case of a state. So before that, I need to maybe remind you that these 0, 0 states right? So all this now lives in the 4-dimension Hilbert space. And the basis vectors in this space now states 0, 0, which is 1, 0, 0, 0, right? State 0, 1, which is 0, 1, 0, 0. State 1, 0, which is 0, 0, 1, 0. And state 1, 1. So it's a new basis vectors for our four-dimensional Hilbert space. 4 vectors. And corresponding coefficients C00, C01, etc., they are the projections of the vector on these basis vectors. So now let's consider a particularly important case when so what if C12 and C21 is equal to 0? Okay. One example of such a state would be this omega capital state, and this state gets a unique name. So let us write the state first: 1 over square root of 2, and then so this 1 over square root of 2 is the projection coefficients. Okay, and the basis vectors left equal to 0, 0 and 1, 1, because the projections 1, 2 and 2, 1 is equal to 0. It's 1, 1 here. So this state is known as a Bell state. Bell state, and it is known as the most entangled state. So it's a let's say most entangled state. So what is entanglement? So what is entanglement? First, let us consider one example. An example is like state like 0, 1 plus state 1, 1. Okay, so it's this is superposition of two states in a superposition of two basis states in a 4-dimensional Hilbert space. And now is the question: is it entangled state or not entangled state? And in order to answer this question, we need to check if this state is separable. Okay, so if we can write this state as a product of two vectors, one belonging to one qubit, one state, one subsystem, and another belonging to another subsystem. Okay, and in fact, this state can be indeed written as a product of two vectors, vector 0 plus 1, and the second vector is vector 1. Okay, so when you take the product of this 1 to 0, you get 0, 1. If you take a product of 1, 1, you get state 1, 1. So it is a separable state. Separable state. So you can separate the vectors. Okay, so that's why the name, hence the name separable separable state. But in contrast, state like 1, 0 plus 0, 1. Okay, so it's another superposition of two basis vectors. Okay, we can consider this one. And what is important here is that we cannot separate this vector. So it's still vector in the 4-dimensional Hilbert space, but now we cannot separate this state into two, in the product of two vectors, right? Like if I would write something like 1 plus 0 times 1, this is the state what we got above. If it's 1, 0 plus 1, 0, we would get 4 terms here. So this state cannot be separated as cannot be written as a product of two vectors. So it's a not separable state, not or inseparable, not separable state. And this is the essence of, or this is the meaning of the entanglement. The states are entangled. Entangled. And a state like this is a perfect example of entangled state, non-separable state. The state above, 0, 0 plus 1, 1, which we called Bell state, is another non-separable state. You cannot write this state as a product of two vectors. Okay. Yeah, so this is basically about entangled states. And yeah, and maybe as a conclusion, concluding this part, a statement that one qubit needs 2D Hilbert space to be considered, right? So it's 2 to the power of 1 components. So 2 components qubit. A system of 2 qubits needs 2 to the power of 2 components, which is 4. And this is the case we discussed just above. And this is 4-dimensional Hilbert space. Okay. Likewise, 3-qubit system would require 2 to the power of 3 components, which is 8. And it's 8-dimensional Hilbert space, and etc. So, for example, n-qubit system would require 2 to the power of n components, and this is the n to the power of 2 to the power of n dimension Hilbert space. For example, a system with typical number of qubits in a modern state-of-the-art quantum computers is around 100. So the state of a resulting, of the result of the quantum qubit is, or the Hilbert space that we need to use to describe the state of a quantum computer with 100 qubits is indeed really large. It's a 2 to the power of 100. So it's the number is really huge. And still, using such big vectors allows us to to use the concept of quantum parallelism when multiple realizations are executed simultaneously in parallel. Okay, so let's write hence quantum parallelism. Parallelism. Quantum parallelism. Let me repeat this part again. So we start from a qubit. A qubit is a system that can exist in two different states. Okay, and quantum mechanics requires us, and this is the postulate number one. It was postulate number one. The statement that before we measure the qubit state or quantum system state, we have to consider the system living or having the both states at the same time. Okay, so a qubit has two states, and if we before the measurement of the qubit, we need to like take into account the both. We have to consider the qubit like being in the both realizations simultaneously. We can measure the qubit and it will collapse spontaneously into the first one in the first state or in the second state. And we cannot predict the result. What we can predict is just probability of finding either state 0 or state 1. Okay, but before the measurement, we need to take into account the both. Now we bring the second qubit to the system, and our space, our vectors become 4 components, so 4-dimensional vectors. Okay, but the principle here is the same. Before we measure the qubits in the system, we have to consider them living in all 4 possibilities simultaneously, all 4 possibilities. Now, if our system is 100 qubits system, then we get a huge number, and we have to consider the system living in all these 2 to the power of 4 different possibilities, different realizations simultaneously. And then we can start measuring different qubits or parts of the qubits in this array in the system and get different results. So this way, we can kind of run several or multiple simulations at once, at the same time, exploring all different possibilities in the system. Okay. Another point to maybe highlight here is this Bell state. So let me rewrite it here. So the Bell state is 0, 0. Let me take another one. 0, 1 plus 1, 0. Okay. So here we have a system of 2 qubits. This is the state of the qubit 2. This is the state of the qubit 1. This is the state of the qubit 2. This is the state of qubit 1. Two different realizations. We take the superposition of both, And this is the state that we can realize, and actually we will prepare quantum computers in this state using this IBM quantum platform. We're going to discuss it today. Okay, so you prepare this state, okay? And then, but physically you still have a system of two qubits, but they like interact. This is the qubit 2, this is qubit 1. And then you can decide to measure this one of this either qubit, either one. So for example, you measure the qubit 1, this one, okay? And there are two possibilities here. You can find this qubit either in the state 0 or in the state 1 after the measurement. And what happens to the qubit number 2? So let's say you measured the qubit 1 in the state 0. So what is the realization? Which part of this state vector represents this realization? The one with the 0 for the first qubit. This is the one. Okay, and this means automatically that after the measuring the first qubit and finding the qubit in the state 0, the psi vector, the state vector of the entire system of two qubits will collapse automatically to the state 0, 1, 1, 0. Okay, and we automatically conclude that the state of the second qubit is 1. Even without measurement, we can conclude, we see that the state of the second qubit is state 1. Likewise, if we get, for example, state 1 for the first qubit, then the system collapses to the state 0, 1, because this is the result for measuring for the measurement of the first qubit. Then we automatically conclude that the second qubit is in the state 0. So in fact, this measurement of one qubit makes some effect on the state of the second qubit. Okay, and the one of the most puzzling facts in nature is the fact that this works like, I mean, this picture holds even if the qubits are separated by a long distance. Like you can prepare the system in this state, and then you can like put apart the both qubits. For example, one at the Earth and another one you can send it to the moon, and still measuring one qubit here locally, you can conclude, you can find the state of the second qubit, which is located far away from you. Okay, so yeah, so we will, this is the concept of shared randomness, and we will probably discuss this sometime soon. So in the literature, you can find this statement as called quantum non-locality. Quantum non-locality. It means that we have some sharing the quantum state over long distance, and measuring one qubit like immediately affects the state of the second qubit, but being far away from the first one. Okay, so it's a very nice and useful concept for example, quantum cryptography, something that is really used today. So quantum cryptography, in contrast to quantum computing, is the very mature area of quantum physics. and we like really use this concept in real life, like banks or military agencies. They already use the quantum cryptography, and the fact that qubits share this entanglement over the distance. All right, so this is about introduction to quantum. Let me know if you have any questions. Oops, I wanted to make them straight on this. Okay, if not, then we start the chapter number 3, and this is the main one for the course. And the title of this one is Quantum Gates and Quantum Logic. Quantum gates and logic. And the subchapter, chapter 3.1, is the Bloch sphere. Okay, the Bloch sphere. So we use the Bloch sphere to represent a state of a single qubit. So let us start from the general state of a single qubit, psi. It is equal to C0 state 0 plus C1 state 1, right? Where, as we stated many times, C0 and C1, they are complex numbers, okay? Because they contain information about the phase of the states. But still, we can assume that, for example, C0 is real, and all the information about the phase is contained in the coefficient C1. It's like describing, for example, two pendulums. We can consider the phase of each of them, or we can introduce the relative phase of oscillation, for example, the second one comparing to the first one. Okay, so like we set the phase of the first pendulum to be 0, and then the phase of the second one will be the relative phase of the second pendulum comparing to the first one. So something the same holds here. So we can always assume that C0 is real, is a real number, and still C1 is complex. Okay, and we can write this complex number C1 as a amplitude. It's a real valued amplitude C1 dash times e to the power of I and some angle phi. Okay, so it's a general phasor representation of a complex number. We know that when we sum up all the absolute values squared of the C coefficients, we have to normalize the sum to 1 to be able to use these coefficients as the probabilities, and corresponding amplitudes. Ci is the probability amplitude, right? This is the statement number 2 in the previous chapter. This Born's rule. So from here we conclude that the absolute value of C0 squared plus absolute value C1 squared is supposed to be equal to 1. Now we recognize the fact that C0 is real valued, so it's C0 squared plus C1 squared is the C1 dash squared, and times e modulus e to the power of I phi squared is equal to 1. So this modulus of the exponential function gives me 1, and the result is C0 squared plus C1 dash squared is equal to 1. Okay, so what it means? It means that I can substitute this C0 and C1 by some sine and cosine functions, because as we know, this quality sine squared, like some angle x plus cosine squared angle x, is give us 1, right? So this is the famous equality, trigonometric equality equation. So in our case, we're gonna, for the reason to, like, which will be clear later, we're gonna substitute C0 by cosine theta over 2. Okay, so our angle is theta over 2, and C1 is the C1 dash, real valued. So sine theta over 2. Okay, so cosine squared theta over 2 plus sine squared theta over 2 gives us 1 for any theta. And the resulting psi state can be written now as a cosine theta over 2 for C0 plus the phase factor, which is e to the power of I phi, right? And times C1 dash, which is sine theta over 2, but I forgot to put the basis vectors. So let me move it like this. Basis vector 0 and basis vector 1. Okay, so yeah, this formula can be put in a red frame because of its importance. So this is basically the same as this one, right? It's just C0 0 plus C1 1, but written in a using other variables. In this case, it's theta and phi, the two angles. And still, this is the general state, or let us put specifically pure state. So it's a general pure state over qubit. And now we can interpret the angles theta and phi. We can interpret theta and phi as a spherical coordinates on a unitary sphere, and this sphere is known as the Bloch sphere. The Bloch sphere. Bloch sphere. So the phi can be any number between 0 and 2 pi, right? The theta for the spherical coordinates runs from 0 to pi. Okay. Actually, we can include this too, like this. Okay, so now let us draw the block sphere. Let us draw a big block sphere like this. Oops, not good. It's gonna be sphere. Okay, better. And let us put the axis here. For example, this is the one. This is the another one, and finally the last one runs like this. All right. So this is the axis x. This is the axis y. This is the axis z. Okay. This is the origin of the sphere, and any point on a surface of this sphere. Actually, let me also draw it like this. So we see it's really a sphere. Okay. Yeah. So any point on the surface of this sphere is denoted by two variables. One is the angle theta, counted from the axis z, so it's a theta, okay? And the second angle is the angle of the projection of this vector on a axis on the plane xy. So this is the projection. And second angle phi is the angle counted from the axis x clockwise, right? From x to y clockwise. So this is the angle phi. Okay, so this angle phi runs from 0 to 2 pi. So it's like total revolution, right, of the vector around axis z, and theta counted from the axis z, and runs from 0 to pi. Okay, so yeah, so this I mean these variables cover any point on this sphere surface, and we can use them to represent the state of a qubit. So any state of a qubit can be represented by a point on the surface of Bloch sphere. Okay, all right. And so now let us, so this sphere gets 6 poles, right? So this is 1 pole, second pole, third pole, fourth pole, fifth and sixth pole. So 6 poles. on the surface. And let us find the positions of the main basis vectors that we introduced in the previous part of the course. To do so, let us recall the state of the qubit written for the block sphere, the cosine theta over 2 state 0 plus e to the power of I phi sine theta over 2 state 1. Okay, and here it's instructive to recall the Euler's formula for the exponential function. E I phi is actually equals to cosine phi plus E sine phi, I sine phi. So the actual formula, expanded formula, is cosine theta over 2 state 0 plus cosine phi plus I sine phi sine theta over 2 state 1. Okay, so we're gonna use this one to see where are the basis vectors on the surface of the block sphere. For example, let's start from the state 0, right? This is the main one, state 0. State 0. So the state 0, in order to get state 0, we need to get rid of cosine theta over 2 and all these coefficients. So I mean, we need to cosine theta over 2 to be equal to 1, right? So to do so, we need to set the angle theta to be 0, okay? And as we do so, the sine theta is equal to 0, so the state 1 is gone. The cosine 0 is 1, so we get only state 0. And we can assume that the angle phi is equal to 0 too, but it doesn't really, I mean, it's not really well defined in the state 0. So where is the state 0, 0 in on the block sphere? It is here, right? So this is the theta 0 and phi is undefined there. So it's state 0. State 0. So uppermost pole of the block sphere is the state 0, the ground state of the qubit. Okay. So the next state 1. So in order to get state 1, I believe theta must be pi or 180 degrees, and phi again equal to 0. Because theta equals to pi, cosine pi over 2 is equal to 0, sine pi over 2 is equal to 1, okay, and phi equal to 0, cosine equal to 0 gives me 1, so, and sine is gone, this complex unit. So this is the state 1 on the block sphere, okay? So the second one, the second pair of states, it was state plus, right? So the state plus is what? Is it's an eigenstate of the Pauli matrix X, and it was 1 over square root of 2 state 0 plus state 1. Okay. So in order to get this one, we need to set theta to be equal pi over 2, Why? Because cosine pi over 2 gives me cosine pi over 4, and it is exactly 1 over square root of 2. Okay. And if I set phi to be equal to 0, then cosine 0 is equal to 1, sine 0 is gone, sine pi over 4 is 1 over square root of 2 again. So I take 1 over square root of 2 from the parentheses. In parentheses, I get 0 plus 1. So this is the result. And likewise for the state 0, which is 1 over square root of 2, 0 state minus state 1. Again, we need theta to be equal pi over 2. Okay, but what is phi? What is phi here? So now we need to get minus for the cosine, minus for the cosine, and in this case phi is equal to pi. Okay, so phi is equal to 0. Cosine 0 is 1. Cosine pi is minus 1. So indeed we get minus in this case. So theta pi over 2 phi is equal to 0. Where is it? It is this point, this pole here, right? So it is the state plus, and phi is equal to pi. This is this state, this pole. It is the state minus. Okay, so we define the 4 of 6, and we have the two other poles. So the first one is plus I. I remind you that this is the state 1 over square root of 2, 0 state plus I, imaginary unit, state 1. Okay. So obviously theta again must be equal to pi over 2. But now phi, we need to get this I here, right? This I. So now phi is equal to pi over 2. So cosine pi over 2 is equal to 0, is gone. Sine pi over 2 is 1. So we get only imaginary unit left there. And indeed, this is the resulting state. So the phi is equal to pi over 2. Okay. So theta pi over 2, phi pi over 2 is this state here. So this is the state plus I. And then obviously this will be a state minus I. In this case, we need minus 3 pi over 2 for the phi. Right, so the last one, state minus I is equal to 1 over square root of 2. 0 minus I state 1. And we need theta pi over 2 and 3 pi over 2. Pretty good. So we define all the basis vectors on the surface of the block sphere. Okay, so these are the basis vectors in the two-dimensional Hilbert space. And one single block sphere represents all these 6 basis vectors. And of course, block sphere represents any other possible state of a qubit of two-dimensional in a two-dimensional Hilbert space. Important point to notice here is that in the Hilbert space, the conjugate basis vectors, for example, state 0 and state 1, they are orthogonal, right? Because the inner product of 0 and 1 states gives us 0. They supposed to be orthogonal because they are linearly linearly independent vectors in a two-dimensional Hilbert space. But on the surface of the block sphere, they are not orthogonal, right? They are kind of collinear. So the vectors or states so the orthogonal states on the block sphere represented by the opposite states on the surface of the block sphere. Okay, or one can say also that on the block sphere the angles are twice as large as in the Hilbert space. Okay, so 90 degree becomes 180. So let us write this note. On the Hilbert on the block sphere, the angles are as twice large as in the Hilbert space. In the Hilbert space. Yeah, so this is all about block spheres, and unfortunately today I don't have time to go to the quantum gates, but we will do that next time. And to do so, I encourage you to go to this website, this IBM quantum platform. Guys, do you see my screen? I'm sharing the screen with the website.
Yes, sir.
Okay. So yeah, here is the IBM quantum platform website. Please go here and create your IBM ID. Okay. Of course, I already have one for myself. Let me quickly go to my system. So this is my education account, the one I use for teaching, basically for teaching quantum. And so as you registered in this system, you can go in, and this is basically the system we will be using for quantum simulations. Okay. So for the simulations, you will need to get this IP token. So this IP token is a specific number that IBM uses to provide the quantum machine resource to your account, let's say this way. Okay, so you use this number to reach out to the quantum computers. Here, what is important, and I suggest that you look through and start playing around with these two resources here. One is IBM Quantum Composer, another one is IBM Quantum Lab. So let's look at the Quantum Composer first. So this Quantum Composer allows you to basically design a quantum program or quantum algorithm of basically any kind, okay, using different gates. So we will discuss the most of these gates next week. Okay, there are two kinds of gates here. One is single qubit gate and multiple qubit gate, like 2-qubit gate or 3-qubit gate. So this line here represents the sequence or execution of the particular qubit. So for now, I have only one qubit in the system. I can add another qubit here. I can add yet another one, as many qubits as I want. And you can see, so when I add more qubits, how scales the Hilbert space. Okay, so for example, for the state vector, representation here, I have, for one qubit, I have only two possibilities, state 0 and state 1. Okay, so this is exactly what we have been discussing. And if I add another qubit here, I've got the 4-dimensional Hilbert space. If I add another qubit, I've got 8 different states, 0, 0, 0, 0, 0, 1, 1, 0, etc. So on the panel on the right, we see this sphere, but this is not the block sphere. This is called Q-sphere. This is something that IBM invented specifically for representation of the states of a system with multiple qubits. Okay, so the block sphere that we discussed today represents nicely the state of one qubit, but it fails completely if you need to represent the state of 2 qubits or 10 qubits or 50 or 100 qubits. And but still, to be able to represent the states of the system with multiple qubits, IBM uses this Q-sphere approach. We will quickly discuss this next time. And yeah, so basically applying these different gates to the qubits, for example, one 1-qubit gate, 2-qubit gates, we can create different states. You see, we can basically manipulate the state of a system. Okay, and another useful point is that this composer, as you add several qubits here, right, it automatically creates the Python code. So you see this IBM Qiskit uses the Python as a programming language. Okay, and here you can basically create the program like this. So it's a program. Now I can open this program in the Quantum Lab. So it's the second resource on this website, which is, server not running. Not sure what's event log. Automatically it's ready for you. Yeah, so for some reason I am not allowed to use it right now. Maybe re-login to the system will resolve this this problem. Yeah, IBM Quantum Lab. Yeah. So basically, IBM Quantum Lab is the main platform we're gonna use to write quantum programs and execute them using quantum computers. Okay, and you see already this the program that we created in the quantum in the composer. Okay, and also here on this website you can look at the number of, you can look at the available machines. Okay, so this is the table of all the quantum computers that are basically ready to use. You see, some of them are online, some of them are online but with some restrictions, some of them are offline, maybe testing, something like that. Yeah, so these machines, these are all IBM quantum computers, and in order to execute your quantum programs, you can basically use either one. The machines differ in terms of the number of qubits. You see, for example, this one gets 127 qubits. And of course, we can look at the other parameters here. And yeah, and these two key numbers that we discussed today, this T1 and T2, you remember the dephasing time and decoherence time. So D1 is the decay time, the time of the decay of the energy, and the T2, which is smaller, right, than T1, is a decoherence time. So main parameter here, I would say this T2 parameter, and this 164 microsecond is the time, like the maximum time of the execution of the quantum of this particular quantum computer. Okay, so this is the architecture of the computer. So here you can see basically all these 126 qubits, 127 qubits, including the 0 one. Some of them are apparently broken, right? Like this one, 120 seconds is a redoubt assignment qubit. Yeah, so the fact it's in different color, I think it's because it's broken or something. Yeah, so this architecture of the computer. Of course, you can look at the others. This IBM QUIF. You see, like the architecture is similar. Here we have like 2 qubits, non-functional. The T2 time is much smaller here. So even though the number of the qubits is the same, you cannot use, for example, this one to run like two complicated programs using this one because the time is smaller. The time is smaller, and etc. So yeah, we will discuss in more detail this IBM quantum platform next time. Now I encourage you to register yourself in the system and start basically play around with it, so you are prepared for the next lecture next week. So let me stop recording now.